Welcome back. We're in CV questions and problems. Problem number 3. A horse canters away from its trainer, so canters meaning it's a type of like trot, away from its trainer in a straight line, moving 130 meters away in 14 seconds, then turns abruptly and gallops a little bit faster, halfway back at 4.8 seconds. You know it's faster because look at the time there. It goes halfway in 4.8 seconds. Well, half 14 is 7, and it does it even quicker, 4.8. So it must be a faster pace, a gallop versus a canter. Anyways, calculate the average speed and its average velocity for the entire trip using away from the trainer as the positive direction. All right, so let's draw a picture first. Yeah. So let's see if I can draw a horse here. Line of the horse. You're trying to draw it too. Oh, that's not so bad. The other one going on here. Well, it needs to be thicker, right? Horses got more girth to them. Like a really muscular leg of a horse. Art class with Mr. Wishway. Gosh. Oh, it's not so bad. I don't know. Can I do a head? Oh, gosh. Oh, gosh. So they got like a jawline, right? Like a jawline, and then it like comes in and then goes down. I don't know. There's like teeth or something right there. Teeth. Got a nose that comes out. That looks like a fierce dog. Wow. There's an eye there. It's like looks like a cross between a werewolf and a horse. Okay, so it's got a tail there. Well, whatever. You draw the best horse you can. It's apparently I need to study how to draw. I give him a ground to put on. As you can tell, the quality of the artwork isn't really important, but actually getting the idea of what's happening here is obviously very important. So let's say that they start. Let's say the horse starts right here. Let's say that's the beginning of them right there at the 0 meter mark. Why not? We'll throw a position scale in here. So here's my position scale. Position axis, you might say. Positive we'll say to the right, negative to the left, as we usually do with any number line. So he moves away from the trainer at 130 meters. So, okay, so let's have the trainer over here. Yay! And the trainer's got like a helmet on because he's a rider too, right? Okay, there we go. So he's going away from the trainer, so that would be to the right in this case. And notice if you drew this in reverse where it's going to the left, you'd get the exact same thing. So he goes 130 meters to the right here. So if he's going to the right, let's go ahead and let's mark out where 130 meters might be. And we're just making this up, so I'll put it anywhere that's in that direction. And maybe I'll even like put like a line of which way he's going, and maybe I'll just kind of show this. And I'm just kind of making up like how I'm doing this along the way here. But he goes over there, and I got little arrows to show that he's going that way. Again, there's no standard way to do that. It's just me making up, so it kind of looks like it. I can visually see what he's doing. And then he turns around and goes backwards, and he gallops halfway back. Well, halfway back, 130 divided by 2, that's going to be 65. So about halfway back is somewhere right in there. So I'll put 65 meters. So then he turns around, so I don't know, maybe I'll show it like that, and then put a little arrow so I remember that he's going this way. And then maybe he ends right here. I'll even label that with end, and it goes that way. Okay, sweet. So I've mapped out what he's doing here, and maybe I'll even put the times in here. So like the time when he gets over here is 14.0 seconds. And now what's the time when he turns around and gets to the 65 meter? Well, it's 4.8 seconds later right? So I got to add the 4.8 to the 14 there, and so now I get 18.8 seconds. Okay, cool. Let's go. I'm gonna graph that too, because graphing that can be very helpful. And it's, we're doing practice problems here, so we can get good practice at this stuff. And that sounds like good practice too. So let's go ahead and let's graph that. I'll go ahead and put the 130 meter somewhere around there maybe. And so let's see, where does he go? Well, he goes from here up to here, and that's 14 seconds. And so he goes in a straight line because he goes at one speed, right? It says that he canters away, so he's just going one speed. Here's the canter. And then he turns around and goes back to the 65 meter mark. So here's the 65 meter mark. And then I got to put the 18.8 somewhere around there. And so then I go and put a point there. So because he ends at the 65, right? I can even see that on my little pictogram diagram there. So he goes back like this. Now I could even put notes to myself here and recognize that this is like steep, right? And this is not as steep. And we can go calculate that. But I'm putting little notes to myself to remind myself that we already figured out that he's going slow. The canter is slower than the gallop, just from our rough calculation in our head. And now let's go and let's figure out what that is. And actually, if we figure out what that is, we can go plot that on another graph. Let's go make another graph. Because again, wouldn't it be good practice to do? So if you're watching this and you didn't do this originally, you just pause this whenever you come across something that I'm about to do that you haven't done, and then try it out before I do it. And then you can go back and double check yourself and see if you did something similar to me or something that makes sense and equally equivalent as I did. Now we said that they're moving in the positive direction in the first portion here, and I know that because one, the positions are becoming more positive, and number two, the slope on a position time graph is your velocity, and this slope is positive. So I'm going to put some sort of positive slope there, and the slope on that position time graph doesn't change, so my velocity is not changing, and I don't know what the number is yet, but we can go figure that out. Actually, let's just stop right now and go figure that out. And I'm going to show you how to do qualitative. I'm going to actually do the qualitative bit, and then I'll go back and put in the numbers. Now, in the second portion, we already did our quick calculation in our head there that this portion that has the negative slope, where the positions are becoming more negative, is going faster. Okay, so let's tackle one of those at a time. First, it's going, the horse is going in the negative direction. I can tell two ways. One, it starts at a high position and goes towards a low position. You might also say that that's going from a high position to positions that are becoming more negative. They're not negative yet, but if it kept going, yeah, they're becoming more negative. They're getting closer to the negative values. That means that it has a negative slope. Furthermore, just one that has an angle like this, that always has a negative slope. And the slope on a position time graph means velocity. So that means that the velocity's got to be like somewhere down there. Now, where am I actually going to draw that? Remember, we said that this is steeper in the second portion than over here. And the steepness is the how fast. So, well, the how fast is like, that's the numbers that I'm going to put here and whatever number I'm going to put down here. So let me make it up. If I was going to put 4 here, notice it wouldn't be -4 down there. It would have to be something bigger than that. Maybe it'd be like -8 or something like that. And it'd be like further down there. And so I'm just going to make something that's further down there. I'm going to get rid of these numbers because I just made those up. And the point here is that, check this out, the height here, right, is relatively small, and the height in the bottom one here is much larger, indicating that this is going to be a bigger number just in the negative direction down there. So I can quickly look at this VT graph, even without, numbers for my velocity, and go, oh, yeah, it goes one direction at the beginning, kind of slow, and then it goes another direction, the other direction, the opposite direction, for the second bit, and it goes much faster. Okay, so let's put in some of these numbers. Let's figure out what some of these numbers are. And I just erased some of that by accident. So let's do that, and we'll do that in red. Why not? So we'll go and look for this first portion. I'll do that right here. So what's the slope here? So So, well, we know that the slope, any slope, is just rise over run. And rise over run is change in y over change in x in math class, but we don't have y's and x's. We have x's and t's. So my rise is my change in x, and my run is my change in t. So now let's go expand that out. Well, that's like some ending position minus some beginning position. Remember in math class, it's like y2 minus y1. Right? Why did they do the 2 first and then the 1? Because that's how you find the difference in anything, and you always do the second thing minus the first thing. And so that's what we're saying here. This is like the better way to describe some ending position and some beginning position. As you get further in math, they do that more. As you get further in science, you do that more. It's a little bit more coherent when things get more complicated, which as you learn more each year, things generally become more complicated, but then that means that they become more useful too, because our world is a little bit complicated. Okay, anyways, the ending position for the first portion there, look, I can use that point right there. That's my ending position, so that's 130 meters. Minus my beginning position, well, that was right here, and so that's the zero right there. Cool. Now the ending time was 14.0 seconds, and my beginning time was 0 seconds. And so now that one becomes pretty easy, right? So just 130 over 14. So I grab my calculator, so you could probably hear me banging around there, and it's 9.29 seconds. Oh, sorry, not seconds. Wow. Let's look at the units up here. Let me rewrite that. That's 130 meters per 14.0 seconds. Well, what's my unit? Well, my unit is literally, and this is true every time, literally whatever units I have right there. So my unit is just my meters per second. And that should make sense because meters per second, that's like similar to miles per hour, right? And that's a speed that we're used to seeing all the time. And so that's, again, some like distance, or really displacement in this case, per some time there. All right, so that's and I know that my slope here is velocity, so I can label that my velocity. So I can go put that over here, 9.29 meters per second. Okay, cool. And so then we need to do that for the second portion there too. Let me do that in a different color so it doesn't blend too much there. I'll do that right here. So then we're going to do the same thing. I'm going to skip this first, so that you know that slope is rise over run, and so that's going to be some change in x over some change in time. Oh, one of my chargers just fell on the floor. Sorry about that. And so that's going to be some, again, ending position minus beginning position over ending time minus beginning time. And what am I going to use? Well, my ending one for this portion is right here, and so my ending position is 65 meters. And my beginning is right here on the top there, and my beginning position was 130 meters. You might say, can you do that so you have the big number second? And say, yeah, of course. It doesn't matter. You just follow the form here, and it always works out every time. My ending time was 18.8 seconds, and my beginning time, beginning of that point that I picked there, was 14 seconds. We already know what that difference is because it told us in the problem that it's just 4.8 seconds. So 65 minus 130, well, that's easy because the 65 we already figured out was half of 130, so you're just left with the same half. So it's 65 meters, but careful, wait, hold on. You got the small number, then the big number, so that's a negative one right there. And then over my 4.8 seconds. Now, check that out. You might say negative 65 meters. What does that mean? Well, you remember that this bit right here, my delta x, was my displacement. And displacement is like distance, but includes direction. And so that the negative sign right there is just my direction. Now that showed up in the other one right here when we had the 130. I have a direction there as well. You might say, well, what direction is it? Well, I didn't write anything, but you know that it's positive. Whenever we don't put a negative in front of a number, it's a positive thing. And so that direction was positive for the red portion, and now it's negative for this one. And we can tell that because I look at this blue line, and again, the positions start high and get lower and lower, or get closer and closer to negative positions. And furthermore, that the slope is negative, meaning that when I go and calculate this, which is what we're calculating slope, I should get a negative value. And that's where the negative comes in. Okay. So I grab my calculator, I just punch in those numbers, and I get negative 13.54, and again, the unit there is meters per second because I'm left with that. And I know that's a velocity because it's my slope on a position time graph. Now I go down over here and I go, hey, then this one right here is negative 13.54 meters per second. Yeah, it is. Okay, so it's not double, but it's definitely faster by a good portion there too. All right. Well, I would say that's actually a pretty good problem right there. And I think I want to rewrite this because we don't care too much in this course. Well, this course being our COVID now version of this course, we're not caring too much about the nitty-gritty average speed and average velocity. So if you were getting tripped up on this problem because of that, don't worry about that. If you could do all of this, boom, you got everything that we're trying to cover here. But since we're already here, I'll go ahead and do the average anyways, because maybe you're curious here. So my average speed, and it's not that hard, but I'm not going to be asking you that on an assessment if that's the question. We know that my average speed there is just going to be my total distance over the time that I traveled at. What's my distance in this case? Well, I went 130. Let's just add it up here. My distance, I went 130 meters when he was going away from the trainer, and then I went another 65 meters plus my 65 meters when I went back. Remember that distance doesn't have a direction, so I'm just adding up all the positive bits of that. Divided by the time it took to do that, 18.8 seconds. And so now I just grab my calculator and I do that. So I get 195 meters over 18.8 seconds. And then 195 divided by 18.8 gives me 10.37. And that's, again, look at the units there, it's in meters per second. And the average speed, we just did average speed. Average velocity is the same idea, but now we get to use velocity bits. So I don't use distance because that's not a direction thing, right? Velocity is a direction thing, includes direction. But instead I replace distance with displacement because that's the one that's similar to it, but it has direction in there. Divided by time, and that is my average velocity. And remember, displacement's just my ending minus my beginning position. What over the entire thing, let me do that in black. The beginning is right here and the ending is right there. So what's my ending position is 65. And my beginning position was just 0. And I do that over the total time, 18.8 seconds. And so now it's just 65 over 18.8. And we find that that's 3.46 meters. Yeah, that's right, meters per second. And so the average velocity is lower than the average speed there. Why is that? Well, that's because they turned around there. And if he hadn't turned around, he would have gone further and further away from where he began, and so my displacement would be bigger and bigger and bigger. Furthermore, let's look at something else here. Are there highlighters in this? Wait, I think there is a highlighter in here. No, maybe, this is a highlighter. Yeah. Let's check out one more thing. Check out this. Right, that was my distance. Okay, cool. And notice that my displacement here is my 65 minus 0 is just 65. And you go, my distance and my displacement are two different values. What gives? Why is that true sometimes? It's not always true. Well, that's true in this case because here the horse or the object that's moving turns in a different direction. And anytime that you turn and you start going in a different direction, you're going to have your distance and displacement are going to be different values. If you're always going the same direction, they'll always be the same value. Okay, cool. That's it. All right. I hope you have a beautiful day. Take care.